Any more questions? Any more clarification you want? If not, then we will take up an example today. And example will be a very simple example of a steel section. So this is our steel section. The stress strain curve also we are taking very simple. So let us say this is Fy, this is epsilon y. So we have taken a bilinear stress strain curve. Actual curves, you know, there is strain hardening. Okay, we will consider those complications later. At the moment, let's consider a bilinear stress strain curve which has increasing stress, okay, up to Fy, and the modulus of elasticity that is given by the slope of the stress strain curve, that is, let us say ES, and then it becomes flat and it fails at epsilon u. Okay, let us say this section is subjected to moment, pure moment, no axial force, only moment. Okay, then what will be the strain distribution? In this case, because it is symmetric, I can, and the stress strain curve is also same in compression and tension, I can guess that the neutral axis will be at dy 2. Okay, and let us say the strain here is compressive strain and here it is tensile strain, and compressive strain will be equal to tensile strain because it is symmetric. Okay. Now let us take different values of epsilon c and epsilon t and calculate m and phi. So let us first assume at epsilon t is equal to epsilon y by 2. That means I am considering my strain somewhere here. So under this condition, what will be the stress diagram? Still, the stress strain relationship is linear. Okay, so the relationship between stress and strain is linear. The strain is epsilon y by 2, so stress will also be Fy by 2. Okay. Can you calculate C and T? In this case, C will be equal to T, and that will be equal to Fy by 2 into B into D and 1 upon 2. Okay? Yeah, 1 upon 2 I have taken here. So Fy by 2 is the stress. Right. Another dy, because this height is dy. So I can say that it is 1 by 8 Fy Vd. So that is the compressive force. And both triangles are same. So C and T are going to be equal. If both the stress strain diagram in compression and tension was not same, then my C and T I have to equate to get the depth of the neutral axis. But in this case, from the symmetry, I can directly say that it is 1 by 2. And now can you calculate the moment? How much will be the moment? That will be C into JD, and that will also be equal to T into JD. So it is 1 by 8 Fy Bd, okay, into how much is the lever arm? This lever arm 4 by 3. Okay, so from the top this will be dy 2 into 1 by 3. Okay, from here also it will be dy 2 into 1 by 3. So this will be 2 by 3 d by 2 plus 2 by 3 d by 2. So that will be 2 by 3 of d. Agree? So how much it becomes? That becomes dd square by 6 into f by 2. What is this BD square by 6? You remember?
Elastic section.
This is elastic section modulus. So I can also write this as Z elastic into Fy by 2. Okay, and Z elastic depends on BD square by 6, so this depends upon the dimensions. Okay, so it is constant, so this is a constant, and if I have to plot m versus phi, okay, so at this point this is ZE into Fy by 2, and how much is phi here?
C plus 80 by D.
Strain epsilon C plus epsilon D divided by D. And how much was epsilon C? Fy by 2, sorry, epsilon y by 2. That's what we have taken. Plus epsilon y by 2 divided by D. So that is epsilon y by D. Agreed? This is our circle. At this point, this value of strain. Okay. So from this relationship you can see that this is depending on epsilon y, this is constant, this depends upon the strain. So till yield point, we are going to get a linear relationship between moment and curvature. You can obtain at different points and you will find that it remains linear right up to my and phi y. I will call these my dash and phi y dash. Okay, for a reason which I will explain you later. So what is the value of m by dash? Can you tell me? In this case, ZE into alpha. Simply cover of that. It is 8 by 48 BD square Fy, and that is 11 by 48 BD square Fy. So that is 3 by 48 times higher than this. So this curve is going to take a shape like this. Let us do that. This is, and what is the curvature here? I have increased strain to double. So it will be simply 2 times phi by dash. 2 epsilon plus 2 epsilon divided by d. So that will become 4 epsilon by d, and that is 2 times of 2 epsilon by d. Okay, are you with me up till this point? You agree? Be comfortable up to this point? Then we will move forward. Yes.
In between that from y to 2y, in between them hardening is there, that's why slope is changing, that's why
Where is the hardening? Our stress strain curve is elastoplastic.
but curve y is so curve.
You see, is there any steel hardening there?
But after the y taking the curve.
So hardening is not the only reason. Now can you tell me why we are getting moment capacity higher? Why the stress strain curve does not have any strain hardening? Okay, But moment curvature curve is showing a hardening. Why? So even if there is no strain hardening, even then after m by dash the curve will be nonlinear and it will show a hardening. Why it is showing that hardening? Because more and more fibers towards neutral axis are yielding. Okay, only difference here is that these many fibers have yielded. Earlier only the extreme fiber was yielding. Here the inner fibers are also yielding. Okay, till when this can go on? When all the fibers yield. But I told you that yielding of all the fibers will require infinite curvature, which is not possible. So let's try one more case where we assume epsilon c is equal to epsilon t is equal to 10 times epsilon. Okay, let's do that. So our strain diagram in this case, this is 10 times epsilon y, this is also 10 times epsilon y. What will be the stress diagram? Can you plot? Yes. Okay, so you have calculated from the similar triangle. This is 2 epsilon y, so epsilon y, 2 epsilon y is happening at dy 2, so epsilon y will be at dy 4. So same thing you use here, and using the same method, you can now plot the stress diagram in this case. So calculate at what distance from the neutral axis the strain will be equal to epsilon y. Here. So this epsilon y will occur at dy 20. So what will be the stress diagram? The stress diagram will be uniform up to this dy 20. And it will be triangular within this dy 20. And dy 2 minus dy 20 will be how much? 19 y 20 dy, is it? Yes. 19 by, no, not 19. 9 by 10. d by 2 minus d by 20 is 10 minus 1 divided by 70. Okay. So 9 by 20. Okay. So this is 9 by 20. Same is here. Can you calculate C and T? In this case also C and T will be equal. So can you calculate C and T? You can calculate in decimals. 19 by 40. In decimal it is how much? 0.47.
M equal to
Good. You have calculated M also?
299 upon 1200.
Tell me in decimals.
Decimal 0.249. 2.249.
0.249
1.
1
Yeah, for BD square.
BD square F. Okay. Everybody please calculate. That if you get, if anybody is finding it difficult to calculate, please ask me. dy 20 in the that the contribution of extreme fibers in moment capacity is more. Okay. Why you do not have much difference from here to here, whereas here you have more difference? Because when the stress in the extreme fiber is increasing, because lever arm is larger, so extreme fibers are having more impact on the moment. The fibers closer to neutral axis do not have much impact on the moment capacity. So once the extreme fiber will start rupturing, it will fail very rapidly. It will fail. And finally its moment capacity, it will break, it will fall down. Okay. So something like this you are expecting. For us, generally we will consider only up to this point when the rupture starts. We don't want to go beyond.
Rupture start at extreme height.
Extreme height. Okay. So look at this curve. Initially it is straight line till the first fiber yields. What is happening here at m by dash? The first fiber is yielding at m by dash. After that also it continues to take additional moment, and then at certain point the capacity to take additional moment becomes zero. Additional moment. Okay, the capacity, the moment curvature curve becomes more or less flat. Okay, and then this will continue up to the ultimate curvature phi u is reached. That will depend upon epsilon u by d. Now I told you what is the slope of this curve? Ai. Can you calculate in our case how much is the slope? Let us say this Ei, which is the slope. How much you are getting this Ei? Any point on this straight line you can take. You divide moment by curvature. So either you can divide my dash by phi y dash, or the first point which we have taken corresponding to epsilon y by 2, you can take that point also. So you calculate any point slope of this line anywhere, okay, it will be same. So calculate this EI. BD cube by 12 epsilon y. नहीं, alpha ही होगा। Alpha ही हो गया। Okay? How much is f by epsilon y? What is f by epsilon y? E. So substitute that equal to E. What you are getting? So that is ES BD cube by 12. You know the formula for I? That's how we are getting I in the expression for moment, or the relationship for stiffness. Okay? So in this case, because it is, I told you, it is a steel section, there is no cracking we have considered. There is no cracking. The cracking will occur only after this rupture. Phi u is reached. Okay. So here the whole section is intact from start to end, especially till this yielding is occurring. E also remains ES. So EI will be ES into BD cube by 12 in case of steel. Later on, when we will do RCC, you will see that it won't be equal to this BD cube by 12. That will be different. So we will see when we will take up an example of RCC section. But in a steel section, you can see. Now, can you tell me, if I have to determine the yield point of this beam, this section, where is the yield point? Which point you can call as yield point? Is this the yield point? What is, by definition, what is yield point?
When extreme fiber reaches to Fy.
That is not definite. Definition of yield point in steel. When we say, when you are testing a steel rod, okay, when you call it that steel has yielded,
without increasing load causing axial deformation.
it does not take any additional force. Okay, so that point beyond which it will not take any additional force, that point we will call yield point. Is there any such point here? So this is not yield point. This point we call first yield point. Okay, that's why I have not represented it by m by and phi y. I have represented it by m by dash, phi y dash. Okay, and this is point of first yield. This point we call point of first yield, and that's why a dash I have put it. It is not the yield moment. Okay, to obtain yield moment, what we do? We do bilinearization or bilinear idealization. So in bilinear idealization, the actual m phi curve which we have obtained just now, it is like this. We will represent it by equivalent bilinear curve. Bilinear means two lines. So there will be one initial line and another one will be this line. So I will represent it by two lines. Okay. Then I can clearly define that this is my yield point. In bilinear curve. In actual curve, it is difficult to say which point is the yield point. But in this bilinear curve, I can say that. And when I am representing it by two lines, I can draw any two lines. There has to be a standard procedure of defining this bilinear curve. Okay. So there are two conditions to define the bilinear curve. The first condition is that the area under the two curves should be same. Because what is area representing? Under the curve, the work done in loading. Okay. So the two curves should represent the same work done or same amount of energy stored. Okay. So the area under the two curves should be same. Even then there is a possibility that you can have non-unique solution. More than one set of bilinear equation you can get. So for that what we do, that the two curves should intersect. This value we will call my and the corresponding curvature as phi y. Okay. So at this curve, this first line which I am drawing, okay, this will pass through my dash, this first yield curve. If I do that, in this case, my original curve is the straight line of y dash, so two straight lines. The earlier one, the original curve, white one, and the idealized curve, the green one, both will coincide, both will overlap. Okay, because both are lines. But suppose there was a moment curvature curve where this initial portion was also curved. In that case, what we'll do? In that case, with the first line will be drawn as a secant line passing through first yield point, m by dash phi dash. So I will draw inclined line using m by dash phi by dash. Okay, and then using equal area under the two curves, I have to draw the equivalent bilinear curve, and where these two lines are meeting, that point we call as the yield point. So you can see that yield point is a notional point. So yield point in moment curvature curve is a notional point. It does not represent any significant event. What were the significant event? First significant event was when my extreme fiber has reached epsilon y. Okay. Another one will be when my extreme fiber will reach phi u. Okay. In between there is a gradual variation. So it is not representing any significant event. So this is only a notional point. And what it is actually representing? It is representing that sufficient number of fibers in my beam have yielded. Okay. So this is a notional point representing significant yield of the section. And you can see this will be close, this my will be close to mp, but it is not equal to mp. It will be slightly less than mp. You can take it close to mp. If this portion is very long, let us say this teeth, then what will happen? This will be almost close to mp. Okay. Otherwise, it will be slightly lower. So this my is close to mp in case of steel, not in case of concrete. We will see later. In case of steel, because this flat portion is quite large, epsilon u is quite large, so phi u is quite large, so flat portion is quite long. Okay, so there you can see that that second straight line will be almost horizontal. Okay, and in that case my will be almost close to empty. Okay, so in our practice we will be using this equivalent bilinear curve. And if you have to draw the equivalent bilinear curve for steel section, you have to calculate m and phi and at a number of points, or just by few points you can do it. Just now I have told you the conditions. So can you draw this point? How many points you will require if you really want to draw it? Only the bilinear curve, idealized curve, not the actual curve. Because use of actual curve in our calculation later on will be difficult. It will make our calculation complex. If we represent it by this equivalent bilinear curve, then it is going to be simple. Okay. So just if I am interested in obtaining this equivalent bilinear curve, how you will obtain it?
3 points.
Which 3 points?
My dash, my and MB. Oh, MU.
But how to obtain my? Problem है ना? इसीलिए I have given this. You assume my is equal to MP. In case of steel, not in case of iron. So in case of steel, you can assume my close to MP, equal to MP, let us say. If you do that, you have to do analysis only for 2 strain. One is corresponding to m by dash when epsilon reaches epsilon y, and another one ultimate point when epsilon reaches epsilon u. Okay, then you can calculate MP and phi u, and MP you can take as m. So just doing analysis at 2 points, you can get this equivalent bilinear curve in case of steel sections. Okay.
We require the 3 values of phi na, phi dash y, phi y, and the value corresponding to the maximum.
How you will obtain phi y?
Phi y, MP we know, slope we know, and phi y will equals to.
So it will be obtained from this equivalent bilinear curve, no?
Yes, yes.
So you don't need to do section analysis for phi y. Section you need to analyze only at these 2 points. At this point and this point. Rest of the curve you can generate using the m and phi values at these 2 points. Okay?
Sir, while drawing that bilinearization curve, we are passing that line through my dash and phi y dash to get my. Here we are doing just geometrical things to get the curves. The actual thing is that to get the equal energy from this. From this we will get actual values. And why are we doing this?
Why we are doing this? We are doing this because later on we have to use this curve.
No,
अभी कोर्स खत्म नहीं हुआ ना, अभी तो शुरू हुआ है, तो आगे हम लोग इसको यूज करेंगे. And there one choice is that I can use the white curve, another choice is that I use the green curve. Which curve you will prefer?
No, to get green curve from white curve, we have to equate energy.
We are not doing that.
We can
In
calculate.
reality, I mean, theoretically you should do that.
Yes.
But based on experience, we have to obtain this m by is equal to MP.
Okay.
Okay. So in that case, what we are doing? We are taking this curve as horizontal, and this curve we are taking, and the error you are making. Actually, what you are doing? Let me draw it again. The real curve is like this. You are drawing a line here and another line here. These are meeting here. How much error you are doing in energy? This much.
This.
Very small. Okay. So this point you will take as
my.
m by and phi y, where your m by dash and phi y dash are somewhere. So once you know m by dash, phi y dash, you can determine the slope of this line.
Yes.
So you can calculate phi y.
Yes.
How much will be phi y? phi y will be simply my over m by dash, okay, into phi y dash, and my you are taking as mp, and this point as mp into mp and phi u. Okay, so in case of steel structures, it's quite easy. And then we define what we call section ductility or curvature ductility. We also call it curvature ductility. And we represent it by mu phi, and this is simply phi u divided by phi r. In case of material ductility, we have defined strain ductility, mu epsilon, and what was that? Epsilon u divided by epsilon y. So that was giving us the ductility of material. This is giving us ductility of, what do you think? Which is higher, material ductility or curvature ductility? Looking at this graph. The relationship between curvature and strain is linear. Curvature is epsilon divided by d. Okay, so relationship is linear. In case of material, where the material has yielded, when you achieved epsilon y, here. Okay, whereas the section you are yielding here, okay, this is same, phi u same, corresponding to epsilon u. So can you tell me which is going to be higher, material ductility or curvature ductility? Higher. Which ratio will be higher? Phi y is higher or mu epsilon is epsilon u divided by epsilon y, and phi u is 2 epsilon u by d, and phi y dash, not phi y, phi y dash is 2 epsilon y by d. So which one is higher? Phi y dash is more than that or less than phi y is less than phi y dash or more than phi y dash? More. So which is going to be higher? Material ductility. So the curvature ductility depends on material ductility, okay, but it is somewhat lower. So the curvature ductility is going to reduce. Actually, we are not interested even in curvature ductility. We are interested in displacement ductility, which we will take up later. Okay, that will depend on curvature ductility. The displacement ductility will depend on curvature ductility. Okay, how to obtain that we will learn. So, any question up till this point? I have the first tutorial for you. So naturally this was very simple. We will go towards more and more complex sections. We will reach RCC. Okay. But before that, I want you to do one exercise. Let us assume that this section is not subjected to pure bending, but it is subjected to axial force also, PM. So what will happen to this moment curvature curve in presence of axial force? So let us say this section is having an axial force equal to 25% of its capacity. What is the axial force capacity of the section? BD into Fy. That is the axial force capacity. Let us say it is subjected to 0.25 BD Fy. That much axial force is there. Then what will happen to the moment curvature curve? You have to do that. Okay, so that exercise you do at homework, and when we meet tomorrow 12 to 1, we will discuss that. Okay. Now you may stop recording. Now we have the time for quiz. So first quiz, please distribute your, we will discuss everything, but now quickly distribute one on each batch.